Hello, geometry. Um, Section 10.3, some theorems regarding chords. I didn't get any specific requests for any problems on that on that section, but we can still look at the answers and maybe take a look at the problems really quickly in case you did get stuck. Especially since we couldn't hold any video meetings yesterday, although I waited in my Jamboard session and nobody ever showed up, which made me feel lonely and possibly insecure. So section 10.3, and here are the answers for 1 through 17. Go ahead and pause and check. And continuing on, problems 19, 20, 23, and 25, and once again, maybe pause and check. All right. Take a quick glance through these problems. Number one, what does it mean to bisect an arc? Well, I would say it's a point on an arc which divides that arc into two congruent arcs. Would be a point that bisects the arc, and then any segment or um, ray or even line that goes through that point would also be bisecting the arc. Number 3, 4, and 5, we're trying to find the measure of the red arc. So with number 3, um, AB is over here. Now here's what I noticed right away. This central angle is going to be equal to this arc. And then because ED and AB are marked congruently, our new theorem, 10.3, tells us that congruent chords intersect congruent arcs, just like congruent arcs define congruent chords. You could have actually gone through this a different way too. You could have said, oh look, diameters AD and EB create vertical angles. So if this is 75, this is 75. And then because the central angle is 75, the arc is 75. Isn't it nice to have choices? The next problem, number 4, it looks like we have two congruent chords because AB and DB both have the same measure of 34 units. They are congruent segments, and because they're congruent segments, arc AB and arc BD must have the same measure. So I would do 360, subtract 128, and then divide by 2. What would that be? That would be 232 divided by 2. So 116. So I believe what you're going to get is you're going to get a 116 for arc AB and a 116 for BB, but we only needed AB, didn't we? So that should be the answer there. What else were we going to do? Number 5. Well, it looks like FH is bisecting, what was the diameter? It goes through the center, and it's perpendicular to JG. Well, a diameter that is perpendicular to a chord by theorem 10.5 bisects the chord, meaning that EG would have to be 8. That would, I think that was the red segment, wasn't it? Moving on. Number 6. Once again, I have a diameter because it goes through the center that is perpendicular to a chord. That means it has to bisect the chord by theorem 10.5. 10.5 says a diameter that is perpendicular to a chord is the bisector of that chord. Well, if it's bisecting the chord, then that point is the midpoint. Set those two equal to each other. Number 7 basically has the exact same thing. A diameter that is perpendicular to a chord that means it's bisecting the chord. Set them equal to each other. Number eight is actually a little bit more interesting. Number eight, you've got two diameters that are intersecting each other. If you weren't sure they were diameters, notice that this arc is 90. That means this central angle is 90. But then by vertical angles or linear angles, you get a whole bunch of 90s. That definitely tells me that 180 degrees. That's a diameter. That's a diameter. And so if those are diameters, then these guys are all radii. And we know that every radius in a circle is congruent to every other radius. That's one reason that you could set those equal to each other. However, they were probably going for something a little more simple. These are diameters, but they're also chords, and they are perpendicular to each other. And diameters that are perpendicular to chords bisect the chords. So through that argument, these are all congruent, but they're also congruent because they're all radii in the same circle. So a lot of different ways you can approach that one. Number nine actually jumped up to theorem 10.6, which tells us that two chords are equidistant from the center of the circle if and only if they are congruent. And it looks like these are distances. Now, how do I know? How do I know that these are distances? Well, remember the man with his hair on fire postulate. They are perpendicular segments. And then, they do have the congruency marks right there. And so because those two chords are equidistant from the center, they have to be congruent. And that's why I set their measurements equal to each other. Number 10, same idea. We have two equidistant chords from the center, so they have to be congruent. And so we set them equal to each other. Actually, this one was a little trickier because they gave you one full chord, and then they asked you for half of the other chord. And so you could either take half of 22 and set 3x plus 2 equal to 11, which, in my mind would have been probably the easier way of doing that one. Or you could have doubled the 3x plus 2, right? And then set it equal to the 22. Now, that just involves more algebra. You got to distribute before you solve. But really, one step of algebra wouldn't make it a big deal. And then the last problem was very similar. This time, though, we have the congruent chords to begin with. And so because H, G, and EF have the same measure of 15, they are congruent. And because they're congruent, they must be equidistant from the center. Remember, if and only if theorems are biconditional. They work in both directions. And so that means that 4x plus 1 has to be equal to x plus 8. I'm not going to solve all those algebra problems for you because I know you know how to do that. 12 through 14 wanted us to tell us what we knew about AB. Well, number 12 has AB as the perpendicular bisector of chord CD. And theorem 1014 tells us that if one chord is a perpendicular bisector of another chord, then that first chord, in this case AB, is a diameter. So we could say AB is a diameter. 13, we have a chord JH, which is a diameter. Notice it goes through center Q, right? And so because it is a diameter and it's perpendicular to FG, that means that it has to be bisecting FG. At least that's what theorem 1015 tells us, that a diameter that is perpendicular to a chord is the bisector of that chord and the arc it intercepts. So I guess we could also say that FH was congruent to GH. And then finally, number 14, looks like we are using 10.6 again, which tells us that if two chords are equidistant from the center, as this diagram shows right in here, then that would imply that they have to be congruent. So NP is congruent to LM. And by the way, if those chords are congruent by theorem 10.3, arcs NP and LM are also congruent. Moving right along, 15 was a multiple choice question. Which one of these is not necessarily true, right? On my quizzes and tests, I try to either underline that or capitalize it, but not on ACT and SAT tests. You just have to make sure you read them carefully, okay? Is PQ congruent to QN? Well, PQ is half, or at least a part of PN. QN is part of PN. How do I know that these would be congruent? Well, how about because LM is a diameter that is perpendicular to it. So that means LM is bisecting both the chord and the arc that it intercepts. So that's using theorem 10.5 is what we're using there. But it also takes care of these two answers for us. Those both have to be true. So not only is PQ going to have to be congruent to QN, but PM is going to have to be an arc that's congruent to MN for the same reason, because LM is a perpendicular diameter. What about NL and LP? Does that have to be true? That would be NL is this guy, LP is this guy. Why would that have to be true? This one's a little more convoluted, but not that much more. So here's the deal. Because this is a diameter, it's cutting our circle into two semicircles, right? Semicircle 1, semicircle 2. But remember, because it's bisecting these two guys, or bisecting PN into those two guys that are congruent, 180 minus something must be equal to 180 minus the same thing. So LP would have to be congruent to LN, and furthermore, because the arcs are congruent, the chords would have to be congruent based on theorem 10.3. So B would have to be true. So the only one left is D. Does PN have to be congruent to PL? I'm assuming this is the answer because all the other ones were true, but let's break it down. Because this is congruent to this, it's an isosceles triangle. So we know that this triangle is isosceles, but is it equilateral? Well, I don't think we know that PN has to be the same. You know, we would have to know that these were 30-degree angles for that to be the case, and they didn't give us any angle measurements, so I don't think we can go quite as far as saying D must be true. It might be true, but I don't think that it has to be true. So your answer on this one is D. What's wrong with 16? Well, CD and EF are equidistant from the center. So that implies that they had darn well better be congruent. But I'm pretty sure that 6 plus 6 is not equal to 7 plus 7. And so the chords are not equidistant, but they should be. Or the chords are not congruent, but they should be because they're equidistant from the center. Number 17, what's wrong with that picture? Well, somebody made an assumption that DC and BC were congruent arcs. That would only be true if this segment, this other chord, was a perpendicular bisector. And it certainly is bisecting DB. There's no doubt about that. But it does not indicate that it's perpendicular. And so, just as an example, you know, look at this chord right here. It's a little more extreme. That's bisecting that chord. It goes through the midpoint, but it's certainly not cutting into two congruent pieces. I mean, look at that piece and then look at this piece. They're not even close. And so you only have one of the two necessary ingredients for that to be true. 18 through 20, let's take a look at those. Determine whether or not AB is a diameter. Yes, it is, because look, it's perpendicular to CD and it's bisecting CD. And if it's a perpendicular bisector of a chord, it must be a diameter. So this one would be yes. I would also argue yes on number 19 because this is an isosceles triangle here. This angle bisector is also a median, so that means we're getting bisected, and an altitude. So this goes back to a theorem from the fall. But there you go. AB is a perpendicular bisector. That means AB has to be a diameter based on theorem 10.4. I think I have a bigger picture of that one right here, right? This is what we were talking about. A little review. In most triangles, your altitude, which is the purple segment, your angle bisector, which is the orange segment, and your median, which is the green segment, are all three distinct segments. But in an isosceles triangle, they all are exactly the same segment. And that's the situation we had here that helped us verify that AB was a diameter. On the other hand, this time I don't think AB is a diameter, because based on, I mean, it is perpendicular to CD. You can't argue that. But based on this triangle I see right here, isn't that the old 3, 4, 5 primitive? I think it is. And so if that's a 3, 4, 5 primitive, and ED is 4, then E is not the midpoint of CD, and that means AB is not bisecting CD. Remember, there are infinitely many chords in here that might be perpendicular to CD, but only one of them goes right through the middle, and it's not AB based on what we see. So there you go for number 20. I think the next one you did was 23. 23 was interesting. This one was actually not just a geometric argument, it was a number theory argument. So let's take a look at it. We know that x plus y plus y, I just made up x and y. I guess you could have said AB plus AC plus BC, but I called AB x, and I called AC and BC both y because remember, congruent chords intersect congruent arcs, okay? So x plus y or x plus 2y is 360 because those three chords make up the entire circle. Here's where it becomes a number theory argument. Because they told us up here that y is an integer, so that just means a whole number that's going to be probably between 0 and 360 for sure. If I multiply that integer by 2, it must be even. Now, that's the definition of an even number, a number divisible by 2. So if I'm multiplying by 2, it's definitely divisible by 2, right? But here's the thing. 360 is also an even number. Now, this goes back to simple number theory you used to talk about in elementary school, right? What happens if I add two odds, like 3 and 5? Oh, it equals 8. That's an even. What if I add an odd and an even, or an even and an odd, like 7 plus 2? Well, that's 9. That's always going to be an odd. On the other hand, if you add two evens, like 6 plus 10, 16, you always get an even. And you can prove those quite simply, algebraically, but we don't have time to do that. So what we have here is we have a case where I'm getting an even answer, which means I either have to be adding two odds or two evens. Well, since we know one of these is even, the other one also has to be even, and we just proved this this case, which it said is if we know that AB and BC arcs have integer measures, then X must be even. This did it. The concept of talking about the evenness or oddness of numbers is called parity. So parity arguments are a big deal in discrete mathematics and in number theory. Parity is a word that describes the evenness or oddness of a number in mathematics. It has other meanings outside of mathematics, like if all the teams in the NFL have parity, that means they're relatively even in strength, right? There aren't any super weak teams or super strong teams. That's what parity means in the real world. So it kind of has a similar type connotation. All right, last problem, 25, and it actually turned out to be an easy one. This is a new logo that this manager wants, and to get symmetry in her logo, she wants arcs AB and BC. So that would be this arc and this arc to be the same. Well, what does that entail regarding segments AB and BC? Well, if we take a closer look at this, we know that um, the entire shape here is a circle, right? And so AB and BC are chords in the circle. And if the arcs are congruent, that they intersect by theorem um, 10.3, we know that the chords have to be congruent as well. So that's really all they wanted you to do is apply theorem 10.3 and come to that conclusion, which I'm sure you did. No submarine problems today, which is good because I'm a little bit claustrophobic, as it turns out, and that would be a little bit weird. So we'll be talking about some more theorems tomorrow. Some interesting angles is what we're going to be talking about. I hope this is helpful, and y'all have a good Wednesday.